Hello and welcome to this presentation on poor installation practices. So just pretty much a guideline on what to look out for and what not to do when installing Daikin products on site. I'm going to start off briefly with safety. Here we can see a nitrogen bottle standing at around 300 bar, pressurized without a pressure regulator. Here the installers have just put a normal oxyacetylene hose with purely regulating with almost 300 bar just by throttling the isolation valve. So we can clearly see there's no pressure regulator on the nitrogen bottle. What's going to happen, you're going to have very serious personal damage, as well as damage to the field pipework, as well as your equipment. And here you can see these are the actual gauges that were taken off this site. And you can see the sight glass exploded in the guy's face. He also damaged his gauges due to almost 300 bar of pressure flying through the hoses. Here we see we must never ever pressure test with oxygen. Oxygen is required for combustion, and under high pressure in contact with oil, the diesel effect is deadly. So pretty much what's happened here, there's refrigerant oil within the pipework. The oxygen has come out under very high pressure, and that pressure has acted like a piston effect, and under high compression mixing with the oil, you reach flash point and the oxygen combusts, and it blew up this evaporator, throwing all the shrapnel possibly into the technician's face. And here you can see an accumulator that also exploded. So you also never ever test with oxygen. And also, just as a note, when you put your oxyacetylene regulators on, you never ever put oil on the thread of the regulators. If it's battling to turn into the bottle, you never ever put oil, because the same thing can happen. As you open the pressure to the oxygen, you could have a catastrophic explosion and a fatal injury as the oxygen combusts with the oil under high pressure. All right, let's take a look at some field pipework failures. Here we can clearly see the incorrect insulation diameter of the armor flex has been used. Here it's also been highlighted, and this is ultimately going to result in very poor thermodynamic properties of the refrigeration circuit. Piping insulation being reduced here with cable ties or tie straps, and that's ultimately going to result in freezing and ice buildup. Because you've reduced the cross-sectional area of the insulation material, these tie straps and cable ties are ultimately going to act as mini evaporators. So in humid environments, there will be water dripping. It's going to damage ceilings, and if it's in an open environment, let's say in a car park, all the humidity in the car park is going to create evaporation, and these are going to drip and they're going to wet the floors and create slippery floors in undercover car parks. Here I've highlighted refrigerant piping not fixed by hangers or supports, it's just lying loose in the ceiling. And ultimately this is going to allow for lateral movement, a left and right movement. Some of the refrigerant travels at between 2 and 6 meters a second through pipework, and ultimately with lateral loading you're going to create pipe fractures, especially on the bends where they come through, and you ultimately end up with a refrigerant leak. Here we can see a site where there's just open pipework in the field. So what's this going to do? It's going to allow for an ingress of debris and moisture, which is going to result in refrigerant oil becoming contaminated and eventual compressor failure. Here you can see there'll be a lot of dust going into the pipework. When the dust mixes with the oil, it forms a grinding paste, and it will damage the running surface of the bearings in the compressor. Also, a lot of moisture going in. If you don't achieve proper vacuums, you will have your oil turning acidic and eating the insulation of your stator within the compressor, and you're going to end up with a short circuit. So it's very important. You have to close off all pipework on site. You can even get little bits of metal or plastic going in the pipework. It will ultimately be captured by the filter, but it is not an ideal environment. Very, very dangerous for the longevity of the system. Here we can see inappropriate pipe supports. You can see the insulation's already been damaged. The brackets are eventually going to cut into the softer copper and create refrigerant leaks. That is most definitely happening already. So do not use metal straps to purely support refrigerant pipework. Here we see inappropriate pipe supports. It's damaged insulation. Here the brackets will clearly chatter through and cut into the softer copper, and also creating a refrigerant leak. These are going to, as the refrigerant comes out at 2 to 6 meters a second, depending on the velocity that the compressor is rotating at, it's going to create a left, right, left, right, left, right motion, and you're going to eventually get cracking on the bottom, on all the elbows, on the bends. You could also ultimately get sagging. Here you can see this copper pipe is already sagging due to no pipe brackets and no supports. So this is a very, very poor installation practice. Vacuuming. Always change your vacuum pump oil. Vacuum pump oil is extremely hygroscopic, so it absorbs moisture very quickly and readily. Oil saturated with moisture will no longer be able to dry out any field pipework. And that's, just remember that that's what a vacuum does. It boils moisture. It lowers the atmospheric pressure in the pipework. And whatever's moisture is in there, because of the low atmosphere, it's going to boil. And that boiling is going to be a vapor, and your oil absorbs the moisture, the vapor, and that causes it to go white. So you must always make sure you have new vacuum pump oil in. A vacuum pump is purely there to lower the atmosphere and cause liquid to boil. It is not like a vacuum cleaner that it sucks. It doesn't work like that. It's a boiling process. And the oil has to be best qualities so it can absorb the moisture that has boiled off in the field pipework. We go on to some brazing and have a look at this brief video. So brazing with nitrogen and without nitrogen. At the top, no nitrogen. At the bottom, with nitrogen. And you can see as we touch the flame here, the deposits, oxide deposits busy flaking as the carbon has oxidized out of the air. When the flame was pulled away on the bottom unit, the nitrogen provided enough of an atmosphere to prevent oxygen and carbonization on the copper. On this example, there was too much nitrogen flowing in the pipework, way above atmospheric pressure. It must just be a very, very gentle puff on your hands, just slightly above atmosphere. If it's too pressurized, the nitrogen, it's going to bubble off all your filler material, and you're not going to get good penetration oils. Also here too, you must never use any brazing flux when brazing copper to copper. Why? Because there's a high possibility of leakage due to fissures for inexperienced welders. With copper to copper, use a Copper-Tech rod, and you want a nice penetration weld. You do not use any flux. Unless you're using two dissimilar metals like brass to copper, then you can use silver solder, and then you can use a flux. But you do not use any brazing flux when using copper to copper due to fissures, leakage fissures. Here we can see further no nitrogen used that was used by brazing. So oxidization flakes will also now mix with the refrigerant oil and also become a grinding paste. Besides damaging your bearings and your compressors, they will also cause expansion valve seats to be affected. On electronic expansion valve, your valves aren't going to seat nicely on the chamfer, and you're going to get liquid refrigerant leaking through, and that's not what you want. Pressure testing. Here we can see that somebody has pressure test points that have just been brazed vertically into a vertical riser in a building. So the problem with this is when you braze on copper, it anneals the copper, or in other words, it makes it much softer. And it's going to affect the structural integrity of the pipework. There's a very high risk of pressure leaks ultimately and fractures in the pipework due to this practice. You never ever pressure test like this. Never. If we look at this picture, multiple pressure gauges now at the end of the run of all the field pipework. And actually there's nothing wrong with this method. This is the correct method and the correct way to pressure test. At the end of pipework, you don't just go and stub 1/4 inch lines and pressure test halfway in the riser. This is the right way to pressure test. Also very, very important, when you do pressure testing, take a notice or take a recording of the outside ambient air. Let's say it's 30 degrees outside, just make a note that it's 30 degrees, and if you're pressure testing to say 30 bar, you might come in the morning and the pressure's dropped. You want to check on your pressure. You will notice that the pressure gauges have all dropped a bit, and you'll think there's a leak on the system. There's no real leak on the system, it's just the outside air has dropped, and it's also caused the pressure to drop in the pipework. So make a recording of that, and there's normally around a 1.4 psi drop per 1 degree drop in temperature. So if you have a 10 degree drop from the previous afternoon to the new morning, you're going to show just over 14 psi pressure drop, which is about 1 bar. And you're going to think you've got a leak on the system. You don't have a leak on the system. It's purely the ambient air that is dropped in energy. Let's look at locating and mounting of the outdoor units. Here we can see outdoor units mounted on springs. This is not ideal for any DX systems. If it's a contained system like a chiller, it's different, but we strongly discourage mounting any VRV systems on springs because it's going to create stress on the copper pipework. The resonance, the oscillations, it's not good practice. You technically only use springs on package systems, namely rooftop packages or chillers, but nothing where there's field pipework that has to leave the system. Here we can see that this unit has been installed on a badly made pedestal, and it's already cracked and bowed the subframe. Ultimately, when this collapses, there's a very strong possibility that you're going to fracture the pipework. Or the unit's going to drop and run at an angle, and the compressors aren't going to be rotating on a nice vertical axis. They're going to be running maybe 15 to 20 degrees off their center running line. And that is not going to help with your rolling elements within the compressor. Here we can see a unit installed directly making contact with the slab. There's no rubber mounts, and you can already see rust forming. Besides that, there's also going to be vibration transfer into the frame. It's going to be increased noise, rusting of the subframe, and as well as possibility of pipework resonating and creating fissure cracks with time of operating the units. Here you can see these little condensers that have been installed in rows. There's no access for cleaning any condenser coils. There's zero access. You cannot get in behind there to clean. No cleaning possible. This is ultimately going to result in high head pressures running, increased power consumption. Your electronics are going to run a lot hotter. It's also going to affect your cooling performance on the system. So always consider serviceability. Here too, we can see insufficient airflow. It's too narrow. Top discharge, you're just going to short cycle hot air. So this is poor installation practice. Here as well, you can see total is going to be a recirculation of hot air, which wasn't taken into account, and either a supply or return duct running right over this. So this unit system is going to run with very high head pressures. More photos of bad installation practice. Further going to result in high head pressures, a lot of high head and recirculating temperatures. Very poor installation practice. Let's look at some poor electrical installations. There you can see somebody has removed the protection and obviously used a blade, but at the same time they've cut directly through the insulation of the 230 volts. Here you can see this is poor installation practice, having well over a centimeter of uninsulated cable. This is single phase, so you're around 230 volt potential. Here you can see there's no grommets, so with time, these holes that have been drilled are just going to eat into the cables. Here you can see on a three-phase system, the installer hasn't used lugs. There's very poor contact area, and here you can see on your L2 phase, one of the conductors has already popped out. So this is going to increase current draw on the cable, resulting in it running much hotter. Here you can see bad work practice. This is on a VRV system. They decided to put a breaker in the unit, and they screwed a metal plate over here. So with a metal plate, the breaker technically can't break. It can't trip in the event of a fault. So remember the breakers here to protect the cable from burning and catching a light. And here it's not going to be able to trip because there would be a metal cover over this, preventing it from tripping. Here we can see also not good work practice with multiple current carrying conductors mixed with the lower. This is just going to get very, very hot and fuse and weld and create short circuits. Here we can see further supply cables just running through a unit without any grommets, so it's ultimately going to chafe through, damage the cable and create a short circuit. Let's look at some other outdoors errors or poor installation practices. This is pipework related. You can see here how within a very, very short period of time, this is the frame of the unit is going to cut right through the pipework and just going to create a big refrigerant leak. Here in these support trays, the installer didn't consider these sharp edges. These are much harder metal than copper, and it's just going to cut right in and create a fracture, and you're going to lose all your refrigerant. This is also some poor practice, pipework gymnastics. Instead of just bringing the pipework out here straight and up the wall, they've created this S-bend and dog-legging, totally unnecessary and poorly thought out. Here we see there is these pipes purely being supported, or unsupported, I should say. There's no supports. These pipes can just bounce up and down, up and down, up and down. With the coefficient of thermal expansion, these are going to expand. And why the installer did this very, very short radius bend, it's not ideal. You could have just come down here and then distributed off the wall. They did not need to do this very, very sharp dogleg bend. But besides that, they could have taken, if they did have to do that, they could have taken the pipework up here, up this wall, instead of U-turning all the way back and then going all the way up. Totally unnecessary. And also very important, remember that there has to be pipe supports here. This refrigerant weighs, when the units run, the pipes experience a lot of internal momentum running inside of them, plus the weight of the refrigerant. And just with time, and gravity is going to cause these pipes to drop and bend. So you have to support this in protected cable trays. Here we can see a VRV system that has been installed right outside a kitchen extract. So within a very, very short space of time, this VRV is going to be covered in grease, and especially the coils. Coils get covered in grease, they're going to attract dirt, and there goes your thermodynamic transfer properties. Here we can see a bypass line that has been fitted. The fault with this is this pipe must be on the bottom, not on the top. This is a commissioning of a VRV system. So typically when you start the VRV system, you would shut that valve, so no refrigerant would flow through. That would flow through here, go through the dryer and carry on. After a few months of operation, you would shut that valve, and then you would open that valve, and then your refrigerant would flow up, down, and around. The problem with this is oil return. So ultimately you would want the pipe to run on the bottom with the valve, so gravity can support the oil and help you get your oil back to the compressor. If we look at some indoors that have been installed, here we can see a supply and return grill in an office. So you're going to have short cycling of your discharge air, and it creates a very poor delta T's on your coil and give you poor cooling effects. Here you can see your remote sensor is virtually in line with the discharge air, so it's going to give you totally inappropriate readings. A lot of mistakes guys make as well is they install these hardwired remotes, and the sun rises in the morning and it sets and it bakes this remote, and it can go up to like 38 degrees, where it's only possibly 24 in the room. So always consider make sure this isn't in direct sunlight, and also make sure you're not getting the cold discharge air blowing straight on this, because your expansion valve is going to modulate on the feedback. It's going to do averaging on that sensor as well as your return air sensor, and your room isn't going to be cooled properly. Here we can see two cassette units. So the discharge air is blowing straight onto smoke detectors. The risk with that is you're going to get a pre-action coming through on your fire alarm system. A lot of nuisance tripping. The Coanda effect is going to throw a lot of also dust into those smoke detectors, so avoid any direct airflow into a smoke detector. It's very poor installation practice. And then lastly, we can have a look at this condense line for the drain. So that's a drain pipe installation. It is just totally inefficient to remove. You need the P-trap effect, not that effect, and you'll end up getting smells and all of that coming back through the pipework. So that was just a quick and short introduction into what you should look out for and what you shouldn't be doing when installing products. Sometimes you have engineers coming on site and they're just going to make you redo your work. So hopefully some of these videos will have taught you better installation practice on what not to do. Anyway, thanks for watching, and keep subscribing and receive notifications on any of Daikin South Africa's new uploads on their videos. Thanks and chat soon.